All right, so we're going to get into sort of the Lewis dot diagrams that we're most used to seeing, and these are Lewis dot diagrams for covalent compounds. For covalent compounds, they are sharing their valence electrons, so I'll be showing you how to do that. But the first thing we're going to do is learn how to predict the number of bonds an atom is going to make. You're going to find this really helpful for drawing your Lewis dot diagrams. So we're going to start with predicting the number of bonds. So when we're looking at this, atoms will bond in order to reach a full valence shell. The number of bonds an atom wants to make will be the same or be determined by the number of valence electrons it needs to reach a full valence shell. All right, so the number of valence electrons it wants is basically the number of bonds that it's going to end up wanting to make. So again, it's really helpful to know your valence electrons. So family 1 has 1, family 2 has 2, family 13 or boron down has 3, family 14 or carbon down has 4, nitrogen down has 5, oxygen down has 6, the halogen family has 7, and then of course our noble gases typically have 8. So hydrogen is part of family 1, so they have 1 valence electron. Beryllium, family 2, 2 valence electrons, boron 3, carbon was 4, nitrogen was 5, oxygen was 6 valence electrons, and fluorine was 7 valence electrons. We don't have to do noble gases because again, noble gases are already at 8, so they're not going to want to make any bonds because they don't need to fill their valence shell. So a full valence shell, what does that mean for them? So the question is, how many electrons do they want to be at full? Now, hydrogen is our exception because it's going to try to end up looking like helium, and helium is an exception, so it's only going to want 2 valence electrons. So this is basically how many does it want? And it wants 2 valence electrons total, because it's going to look like helium, and helium is our exception. So if it's helpful, you can just write the word exception here. So you remember that is an exception to the octet rule. Beryllium, for super funness, is also going to be an exception. And you'll notice that I already have them starred. These are actually all going to be exceptions to our octet rule. So beryllium is going to be an exception. It only needs to get to 4 valence electrons. Again, if it's helpful, just write the word exception next to it. And then boron is going to be our third exception. Again, instead of wanting to get to 8, it's only going to get to 6 valence electrons. This is not for the family. This is just for these specific elements. So hydrogen, beryllium, and boron. Now, these ones that are double starred, this represents how the family is likely to behave. So that means all the way down to the staircase. So carbon is not an exception. So carbon and silicon both want to get to 8 valence electrons. Nitrogen down to the staircase wants to get to 8 valence electrons. Oxygen down wants to get to 8 valence electrons. And fluorine down wants to get to 8 valence electrons. So none of those are exceptions. These are 3 exceptions that you should know for our covalent compound bonding. All right, so the next one says then how many valence electrons do we need to reach what we consider a full shell? So since hydrogen has 1 and it wants to get to 2, it needs 1 more. Beryllium is at 2. It wants to get to 4. It needs 2 more. Boron is at 3. It wants to get to 6. It needs 3 more. Carbon is at 4. It wants to get to 8, so it needs 4 more. Nitrogen is at 5, or its family is at 5. It wants to get to 8, so it needs 3 more. Oxygen is at 6. It wants to get to 8, so it needs 2 more. And then fluorine is at 7. It also wants to get to 8, so it needs 1 more valence electron. These will then represent the number of bonds that will form. If hydrogen just wants one more, it's going to make only one bond. If beryllium wants two more, it's going to make two bonds. Because boron wants three more, it's going to make three bonds. Because carbon wants four more, it's going to make four bonds. Because nitrogen wants three more, it's going to make three bonds. You're going to find this really helpful, I promise, in the future. Oxygen's going to make two bonds. And because the halogen family wants one more, they're going to end up making one bond. So we're going to use this as part of our strategy for figuring out what the Lewis dot diagram for covalent compounds looks like. And then in addition to that table that we just filled out, I've got a list of additional tips that might make it easier for you to draw the Lewis dot diagrams. The first thing you're going to do is count up the total number of valence electrons per the chemical formula. So each atom is providing a certain number of valence electrons. So you should count up how many valence electrons are available to be used in your picture. A good example of that is this H2O here. So H2O, so hydrogen, we've got two of them. Hydrogen is one valence electron, but I've got two of them. So this is one hydrogen and this is the other hydrogen. So each of them is bringing one valence electron. And then I've got oxygen, and oxygen is bringing 6 valence electrons, right? So that means that I'm going to have a total of 8 valence electrons in my picture. So that means that your picture is allowed only 8 dots. The next thing you want to do is predict the number of bonds each atom wants to make. So again, if I'm looking at H2O, if I look at oxygen and I look at my chart, oxygen has 6 valence electrons. It wants 2 more, so it's going to make 2 bonds. Hydrogen over here on the left wants 1 more valence electron, so it's only going to make 1 bond. So I can predict number of bonds. So each of these hydrogens is going to want to make 1 bond, and my oxygen wants to make 2 bonds. So I'm just taking notes here just so that you can see things I'm thinking about. Whichever atom makes the most number of bonds is going to be our central atom. So if there are only 2 atoms in the whole molecule, then there can't be a central atom. But if there are more than 2, then you want to put one of them in the middle. So that means I'm going to put oxygen in the middle, and then I'm going to arrange the other atoms around it as symmetrically as possible. I like going left to right and then up and down. So I'm going to put 1 hydrogen here to the left and then 1 hydrogen over here to the right. So oxygen is in the middle because it's making the most number of bonds, makes 2 bonds. And I'm putting hydrogen on either side of it. Then the first thing I'm going to do is I'm going to put my bonds in. So a bond is a shared pair of electrons. So it's 2 dots is a bond. So I'm going to do bonds on the left and bonds on the right because that's what makes a molecule, is that things are bonded together. And so far what I can see is that I have used 4 dots and I'm allowed to use 8 dots total in my picture. So now what I'm going to do is, now that I've bonded to each of my neighbors, is that I'm going to look at the number of predicted bonds and see if I've satisfied that. So hydrogen wants to make 1 bond, so this hydrogen is making 1 bond. This hydrogen is also making 1 bond. And funny enough, my middle oxygen is making this bond and this bond, so it's making a total of 2 bonds. So everybody's making the number of bonds that I thought that they would make. But I'm not quite done yet, because the whole point of bonding is that everybody gets to a full valence shell. So right now this hydrogen's happy, because remember it's happy at 2 valence electrons because it was an exception. And this hydrogen is happy because it's at 2 valence electrons and it was an exception, so it's happy there. The problem is that my oxygen right now only has 4 valence electrons and it wants to be at 8. But the nice thing here is that I've only drawn 4 dots and I get 8 dots in my picture. So what I'm going to do is I'm going to fulfill the full requirement for all of my atoms without going over my dot limitation. So I can put my additional 4 electrons onto my oxygen, and now it has 8 valence electrons, and now everybody is happy with a full valence shell. So when I draw this, I can either draw it like this. I wouldn't draw the circles around it. Or I could draw it where bars are drawn instead of a pair of dots. And then all you have to remember is this bar is a pair of shared electrons. Now it gets even trickier. Sometimes what's going to end up happening is that they're going to start making multiple bonds. So if we need to, they might start making double or triple bonds in order to satisfy the number of bonds they want to make. So I think oxygen, O2, is going to be a good example of this. So I'll do another problem with you. So I'm going to erase my H2O example. And I'm going to do oxygen for you right down here. So I'm going to do this example problem. So there's only 2 atoms. There's an oxygen and another oxygen. So I'm going to draw them next to each other. And I'm going to go through all of my steps. So oxygen brings, I've got 2 of them. So they bring 6 valence electrons. So that's 1 oxygen. And then the other oxygen also brings 6 valence electrons. So I get a total of 12 valence electrons in my picture. So that's 12 dots total. I can't have more than 12 dots. I can't have less than 12 dots. I have to have 12 dots. And the other thing that I know is that oxygen wants to make 2 bonds. So this oxygen wants to make 2 bonds, and this oxygen also wants to make 2 bonds. So the first thing I'll do is I would bond them at least once. They have to be bonded in order to be a molecule. Now, I can see already my first problem is that I'm not making my predicted number of bonds. I'll also notice that if I try to start satisfying them by adding in my other dots, I'm not going to get there. So if I try to start satisfying both of my oxygens, they both want 8. So I'll go 1, 2, 3, 4, 5, 6, 7, 8. So this one has 8. I've used 8 dots. 9, 10, 11, 12. Okay, so here's my problem. This oxygen over here only has 6 valence electrons, and this oxygen here has 8 valence electrons. This oxygen to the right is unhappy, right? So this doesn't work. But I can't add more dots because I don't have more valence electrons to add to my picture. So what I'm going to do instead is what I already know is that both of my oxygens wanted to make 2 bonds. So what I'm going to do is I'm going to add another pair of shared electrons. So that's called a double bond. So 4 shared electrons means that it is now a double bond. So now I've used 4 electrons, and then I'll go 5, 6, 7, 8, 9, 10, 11, 12. And what I can see here is if I look at this oxygen, it now has 8 valence electrons. And if I look at this oxygen, it also has 8 valence electrons, but I've only used 12 dots total to get there. You can, of course, draw it with all dots if that is what you like. Or, as you get more familiar with this, each pair of dots is 1 horizontal bar. So that is what a double bond will look like. And you can go all the way up to a triple bond, which would be 3 bars or equivalent to 3 pairs of shared electrons. So what you're going to do is you're going to try practicing some of these problems with a partner, and hopefully you'll get through those example problems and start to make your way through some of these additional practice problems down here. These larger molecules get a little bit trickier. There will be multiple central atoms. Just do your best.